history, we've grappled with various perspectives on the idea of absolute space and time. Surprisingly, it seems the notion of an absolute position is merely a human construct. In essence, the cosmos is a colossal, ever-expanding container filled with celestial objects. Imagine, if you will, the stars, planets, black holes, and cosmic dust vanishing into thin air. All that would remain is the vast, uncharted expanse of empty space itself. But what secrets lie within this infinite void? You know, even very simple things, like you go back to the Greeks, so Aristotle and very clever people, but they thought the Earth was at the centre of the universe. Now, why? Because it feels like we're not moving. And that's quite a deep point, actually, in physics. It's like, why is it that we're flying around relative to the sun very fast, at whatever speed it is, 18 miles a second or something like that, and the whole solar system's going around the Milky Way galaxy and so on? Why is it that we don't feel it? The Greeks quite naturally said, well, because we're at the centre of the universe. They also said everything falls towards the Earth, so therefore the Earth must be at the centre. It's natural. And actually it's quite a deep thought to understand why it doesn't feel that we're moving. You have to go all the way to Einstein, really, for someone to take that very seriously. Well, he said, well, there's a great little explanation in Stephen Hawking's Brief History of Time about this, that the idea that you can't tell whether you're moving or not demolishes the notion of absolute space. So if we think about space, if I say space, you'd think it the way that Newton did, of a big box within which things happen. That's a natural picture of space and the universe, isn't it? It's a thing in which all the planets and galaxies are placed. But Hawking says, well, imagine bouncing a ball. So we bounce a ball on the table now, a tennis ball. So I drop it and I catch it again. So let's say I drop it and it takes a second to bounce up. So in that second, the Earth has moved about 18 miles or so in space around the sun. So you could ask the question, did that ball return to the same place in space or not? And the answer is, you can't answer it. It does from our perspective. But from the perspective of someone watching the Earth go all the way around the sun, when I caught it again, it had moved 18 miles. From some other perspective, it would have done something else. So the point is, you can't say, this is a point in space. It came back to the same place. Because that just depends on your perspective. Depends on whether you're watching the Earth go around the sun or whatever it is. So Einstein said that means there's no such thing as absolute space, which kind of follows if you think about it. But that's it's cool, but difficult thought process. To truly grasp the astonishing nature of our ever-changing position in space, picture a time when Earth resided on the opposite side of the galaxy, as dinosaurs majestically ruled our planet. NASA research scientist Jesse Christiansen shared an eye-opening fact. When dinosaurs roamed our planet, the stars we see today in our night sky didn't even exist. The Sun takes approximately 200 to 250 million years to orbit the galactic center, with the entire solar system nestled with one of the galaxy's spiral arms. Remarkably, the last time our neighborhood was in this part of the galaxy, the first dinosaurs were just beginning to appear on Earth. The Stegosaurus roamed the Earth during the late Jurassic period, between 156 and 144 million years ago. On the other hand, the Tyrannosaurus rex lived during the late Cretaceous period, between 67 to 65 million years ago. The T-Rex actually existed closer in history to humans than to the Stegosaurus. Throughout the ensuing millions of years, these dinosaurs lived and thrived, while our solar system traversed the opposite side of the Milky Way. As we continue to journey through space, we wonder, what beings will inhabit our planet the next time we complete another orbit? The idea of our ever-changing position in space is inherently linked to the concept of relativity. In simplest terms, relativity is the idea that the measurements of space and time are independent of the relative motion of the observer. This means that our perception of space and time is not absolute, but rather is influenced by our position and motion in the universe. And Einstein elevated that to a principle and said, if you're not accelerating, you're just moving at a constant speed in a plane, or now. I mean, that's essentially what we're doing now. We're moving around the sun at effectively constant speed. Then you can't tell. So there's no experiment you can do. We could look at the decay of a radioactive nucleus, or some electricity and magnetism, or bounce a ball, have a pendulum, whatever it is, and there's no experiment you can do to tell you whether you're moving or not. Therefore, that concept has no meaning, because you can't measure it. That's led Einstein to relativity. That's the basic general relativity, which is our best theory of the universe. Newton's laws stated that two frames of reference moving at a constant velocity relative to each other observe the same physical behavior. Essentially, there is no absolute rest frame or absolute constant velocity. Everything is relative, and either frame can be chosen as a reference benchmark. As the laws of electricity and magnetism emerged in the 19th century, it appears that these forces could distinguish whether a frame was in motion or not. However, experiments failed to confirm this. Albert Einstein stepped in with his groundbreaking principle of relativity in 1905, asserting that absolute motion at a constant velocity was undetectable by any physical processes. Einstein suggested that the laws of electricity and magnetism were correct, and it was Newton's laws that needed modification. These modifications only became significant near the speed of light, setting an absolute limit that no material object could exceed. Experiments, particularly in particle accelerators, have confirmed these predictions. As particles approach the speed of light, their mass increases, making it increasingly difficult to accelerate them further. Now, consider the observable universe as a sphere extending outwards from any observation point for 46.5 billion light-years. The farther away we look, the farther back in time and more redshifted the view becomes. This raises a captivating question. What is the shape of the universe? Well, one point is that it's expanding, and we always see the same radiation out there, so the glow of the Big Bang. But there are some deeper reasons. From the theory of inflation, the best way to explain the universe, the properties that we see, is that it's very much bigger than the piece we can see. So, for example, we measure space to be what's called flat. So if you imagine slices of space, let's imagine slices of them at different times. So you just slice the universe, and it can have a geometry, right? It can be flat like a tabletop, or it could be curved like a sphere, or it could be curved in the opposite direction, sort of like a saddle or a bowl. And we can measure that. And when we measure it, we see it's absolutely flat. And that's a very unusual thing for it to be like, because what Einstein's theory says is that the shape of space, that the curvature of space is determined by the stuff that's in it. That's basically Einstein's theory of general relativity. Puts stuff in space and it curves it and bends it and warps it and stretches it and so on. And what we find is that there's precisely the right amount of stuff in the universe to have a completely flat universe. And the explanation, the most favoured explanation for that, is the universe is way bigger than the piece we can see. And that's one of the ideas about the universe and why it appears to be the way that it is, because it's way, way bigger. So we're just looking at a little piece, and that's why it looks flat. But what shapes the very fabric of space and time in our universe? While Newton and Einstein had conflicting theories about how time works, both agreed that time moves only forward. So far, no physical evidence suggests anything in the universe can dodge time. Scientists aren't entirely sure why time moves only forward, but they have theories. One theory hinges on the second law of thermodynamics, which states that everything in the universe moves from low to high entropy, or from uniformity to disorder. The arrow of time suggests that time is asymmetrical, with events progressing at the Big Bang to the chaotic arrangement of galaxies and their inhabitants today. Another theory proposes that the passage of time is due to our expanding universe. As the universe expands, it pulls time with it because space and time are interconnected. However, this implies that if the universe were to reach a theoretical expansion limit and begin to contract, time would reverse, creating a paradox. As we ponder the intricacies of space and time, we can't help but wonder, what does the dimensionality of space-time truly entail? There's a third dimension of space. The same applies, it's just a generalization of geometry. We can picture it in 2 dimensions. You can quite literally, you could imagine sending light beams out. We do this measurement actually. We can look at the most distant light we can see, which is something called the cosmic microwave background radiation, which is, if you imagine looking out, if you look at the Andromeda galaxy, which we can see with the naked eye, it's the most distant object you can see with the naked eye, and it's about 2 million light years away or so, which means the light took 2 million years to get to us. So it's a long way away, but it's very big. So as you look further out into the universe, to more and more distant galaxies, you're looking further back in time, because you look at something that's 1 billion light years away, then the light took 1 billion years to get to us. So you see it as it was 1 billion years in the past. And we can actually look so far out that we can see almost back to 13.8 billion years ago, which is very close to the Big Bang. So we can look to light that began its journey before there were galaxies. And that's the oldest light in the universe, which is, by the way, one of the pieces of evidence when people say, I don't believe in the Big Bang. The answer is, well, you can see it. So we have pictures of it. That light, it turns out that there are sort of structures or ripples in that light, which we can use as a ruler. So quite literally, as a ruler on the sky. And then, because that light's been traveling through the universe, we can see how that ruler has been distorted as the light has traveled through space. And so we can infer whether space is flat or curved, or how it warps, if you like, just from that measurement.